So what I want to do now is to go over how you would proceed to compute a least square solution in a sort of realistic case, and that will be linked to the content of the computer question in assignment 2. So what I'm going to do is show you how we will proceed in the case of the data that we made up the other day, the Canada census data. In the case of the assignment, you'll have to get data from a source that I've indicated and use it. So I remind you that what we've done is we've created this file here, a Canada census, that we've saved both as an RDS file and a CSV file, which contains the census values for the population of Canada throughout the years. And so what we're going to do is we're going to incorporate this data and perform least squares solution to this. So one remark that I want to make, I am not, and I will provide this code to you, but I will stay with not making a lot of comments and not commenting the code so much is what I mean, because I want you to actually go through this process yourself, and I don't want you to just pull a file and use it for your assignment. I want you to sort of try to play with the data and in a way that would work, okay? So I am going to make a new R notebook. And so as I said, I'm not going to comment in the language or comment in the Markdown. So I will leave it to you when you're working through the assignment to add proper code comments or Markdown text to explain what's happening. Here I'm just going to go through the steps that we need to take. So let's start with something simple. Let me load the data by saying that, for instance, I could use read CSV, and the file is called Canada Census, I believe. Yes, and by the way, so if you hit Tab and you're using a function that R knows to be a function that deals with files, for example, then you get this completion menu. So I can simply select from there. I'm going to hit Enter, and that will put canadacensus.csv as a file. So I'll evaluate this. Let me just, again, when we do this, we don't get the details. So it has properly read the file. I have one column which is year, the other column which is population, and these are the numbers that we get. So perhaps so that it's easier to really think in terms of the problems we have seen so far, maybe the first thing we could do would be to say, well, throughout our explanation of how things work, we've been using X and Y. So to make our life easier, let's just say that X is data dot, so that's going to be year. And note that here again, I've used completion, and Y is equal to data dot star population, okay? Oops, evaluate this. So what does it look like? Let us, whoops, what am I doing? I don't know what happened there. Let me just plot X and Y. And perhaps, as I had done before, let me use PCH equals 19, which typically I think means that I'm making big dots. I'm going to make them even bigger. I'm going to make them size 2. Let's see if that's what I wanted to do. Yes, that works. So what do I need to do now? I have this data set. The X and Y are my points, and I want to carry out least squares regression, let's say least squares identification of the two lines. So I'm going to start with trying to find a Y equals A plus bx. And I remind you that, so what I need to do here is create the matrix A, and that matrix A is going to have, so here we're fitting A plus bx, so A and B are our unknowns, and the capital A, so A, little a and little b are the unknowns, and capital A is the matrix that has the coefficients that are in front of A and B. So if you'll recall, and again, so for example, when you're working through the assignment, I'll expect you to explain this a little bit, to make a markdown cell in which you'll say, the reason I'm doing what is following is this or that. Okay, but here, as I said, I'm not going to detail. So I'm going to make the matrix A. And so recall that what happens is the first column of A, in this case, is going to be the coefficient of lowercase a. And that coefficient throughout is going to be just 1. Okay, because it's A plus bx, and so it is every time A just has the coefficient 1 in front. So I'm going to make a matrix, and that matrix is going to have what? It's going to, well, let's make it again. Remember that I've pointed out several times, when you enter a matrix in memory, you can do it by rows or you can do it by columns. We are going to use the fact that we can do it by columns. So what does the matrix have as its first column? Just once. So how am I going to do this? I am going to repeat. And this is another important command in R. Rep is for repeat. Repeat the value 1. And how many times do I want that value 1? Well, I want that value 1 as many times as I have X or Y, okay? As many times as I have data points. So how can I say this? Well, X is a vector, and to know the length of a vector, there's a function called length. So I'm going to repeat, and actually I should start with a C here, because I want to make a vector that has the entries in the first column and the entries in the second column. Okay, so the entries in the first column are going to look something like this, and the entries in the second column are the values of X, okay, because now we're looking at Bx, and so the coefficient of B are the X's, okay, so this is simply X. So let's see, and so this is what the matrix contains, and now I'm going to say that this matrix has as many rows as there are entries in X or Y, and 2 columns. And I'm not using the by rows equals true because I want to do it in column. Okay. And here I'm just going to, once again, fill the matrix and then plot it. So I have a matrix of 23 rows and 2 columns, which is exactly what I want because this data frame has 23 rows. So that means there's 23 data points. So that matrix has 1 in the first column, and the X values in the second column. Okay. I also need to make my vector B. Oops, this is not what I want to do. It's not control, it's just B. I need to make my vector B. What is my vector B? Well, B is simply Y. Okay. And now what do I need to do? I need to make the matrix A transpose A, and I don't know yet if it's going to be invertible or not. I actually have no clue. I haven't run the problem yet. So let's see. So I'm going to give it a name because I don't want to have to write A transpose A every single time. So let's call it ATA, A transpose A. Okay, ATA is transpose of A matrix multiplied by A. Oops, transpose, sorry, I'm mistaking my languages. It's T of A. So I don't know what T of A is, but and I'm not going to show it because this matrix transpose of A times A is going to be, so there's, how many did I say? It's 23 rows, and therefore A transpose times A is a 23 by 23 matrix. We could actually show it, but excuse me, it's not going to be pretty. Well, actually, it doesn't want to show it. Oh, sorry, it's a, oh, yeah, no, it's actually a 2 by 2, sorry, I'm mistaking my dimensions. But it's an interesting point that I was actually going to make soon. There's going to be a problem here, because you see the value of this. This probably means that what is called the condition number of the matrix is going to be very bad. That matrix is going to be difficult to invert. And let's see what the determinant of ATA, oops, I'm not in the proper thing. The determinant of ATA is det, sorry, typing not in front of my face. No, it's not too bad. Okay, so, and, but let's see, so can we invert? So I'm going to call, let's say, again, I'm not in the inverse of ATA is equal to, so remember that to invert the matrix, you simply solve for that matrix. I have no clue what the inverse of ATA is. It's not too bad. Okay, we might have numerical problems. It's yet to see, but okay, it looks about okay. So, in any case, the determinant is non-zero, and if you look at the matrix, you can see, or if you look at these columns, you can see that those columns are linearly independent, and also the determinant of the matrix is non-zero, so we know we are going to have a unique solution, and the solution that we'll get, whoops, I don't know what I did, yes, the solution that we'll get, let's call it sol, it's simply going to be what? It's the inverse of ATA. I've already done the computation, so I don't need to go any further, times the transpose of A times B. And B. Oh, this looks ugly, but and I'll come back in a second as to the reason why this is looking this ugly. But let's see if we can plot this. So to plot this solution, what could I do? Well, I'm going to make the vector. Well, I'm actually let me just take. Okay, so let me go back and copy the plot command here. This way, I already have this. And what I need to do after plotting is plot the line. So this line has equation, so it's a line. And I'm just going to make the line it's a straight line, so it's quite easy. It doesn't need many points to be plotted. And so I'm just going to plot x at the values of x. And at the values of x, what do I get? I get sol of 1. So this is a plus bx. So sol of 2 times x. And I'm going to say that I want my output to be a line. And that's it. Or maybe let's make it a bit fatter, just so that we see it better. Let's make it line width 2, and let's make it red. Okay, so this is the best linear approximation to these data points here. Now let's do the fitting of a quadratic. So if you recall what we did when we were fitting the function y equals a plus bx, we had the matrix A that took the form of 1, x, and if you'll recall, what we need to do now is we want 1x and x squared. So all we need to do here is I'm going to make the same, but here I'm going to add x squared. And the number of rows remains the same, but here I have now 3 columns. So you can see what's happening, and this is going to be quite bad. I mean, the size of these entries is worrying, but let's see if it still works. Then I can proceed exactly like before. I can make, and the vector b doesn't change. I don't need to change this because b is still the y. Okay. Now let's do A transpose A, which is again, so this time it's going to be a 3 by 3 matrix. Where am I? For some reason, I am not getting this. So A transpose A, now this matrix has 3 columns. So when I take the transpose, I get this. Let's see what the determinant of this is. Oops, sorry. Okay, this is getting huge. Likelihood that we'll get into issues, numerical issues here is becoming higher and higher with this type of values. We'll see more about this in later. There you see. Okay, so the system is computationally singular. This is as I was suspecting this would happen in the earlier case, but it didn't. But here we are getting this. So this means that the matrix is very close to being singular. It is not properly singular. So the determinant is not 0, but the determinant is probably very close to 0. And this is normal because you have wildly varying scales of numbers happening here. You have 23 here, and you have a number that's to the power 14. So with 14 digits before the comma, okay? So how do we deal with that? Well, it is actually quite simple. What we can do is we are going to redefine our vector x, because if you think about it, the spacing of the values is really what is important. I mean, so we have every 5 years or every 10 years. So what I'm going to do is, oops, I inserted at the wrong point. I am going to shift the values of x. So x, remember, looks like this. Well, what happens if I subtract from x the minimum value in X. Then you see I have these numbers here. And what's going to happen is when I create my matrix A, those numbers, when I square them, as we need in the third column of A, they are going to be much smaller than when I'm squaring 2010. So let's proceed as we had just done, and maybe what I'll do is I'll do all of them at once. So I'm going to create the matrix A. I am going to create the matrix ATA, which is A times A transpose. I am going to compute the determinant of ATA just by curiosity. And then I am going to invert ATA, and let's see if this works when we do this. Oh, still bad. Wait. I am surprised because it looks like I did not change anything here. Yes, I didn't assign the value. So now I want X, let's call it X new, just to make sure that it's clear what we're doing. So I didn't assign the value here, so here I need X new, and here I need X new. That's much better. I don't know how much better it is, but clearly we're able to invert the matrix here. So now I'm going to be able to compute my solution. So let's see. So now my solution here is inverse of ATA. So that's A transpose A inverse times matrix times the transpose of A times B. And of course I didn't plot it, but never mind. And now what I'm going to do is exactly like I did before. Perhaps we want a few more points. So what we're going to do is change things a little bit. B. So I'm going to continue with this line here. And let me show you one thing we could do. How am I going to do this? Well, I'm going to take, and here there's a little issue because let me plot with X new. So this is going to be a problem because here my X new varies from 0 to 120 or 160. I don't remember what it was. So we need to remember that this is what we're using to plot. This, on the other hand, is X. Sorry, I shouldn't move this one because this one is still using X. But okay, so I could use X new. Let's see if it works. I need to think about this. What do I need to do? The other one that I could plot, well, I'm going to make X. Okay, so X values. I'm going to say that this is the sequence from the first value in X new to the last value in X new, which I find by simply saying this is the value of X new at the length of X new, and I'm going to plot every, let's say, 0.1. And here, what I'm going to do is I'll plot X values, and then I'll plot the solutions as sol of 1 plus sol of 2 times X values plus solution of 3 times X values squared. And I'm going to say that this works the first time around. I'll be very happy. This is type. I want a line, and line width. I want, still in this, line width equals 2, and I'm going to make that one, let's say, blue. Okay, so the red one doesn't work because of this shift that I did. So that makes sense. Let's forget about that one for now. I will actually let you fix it in the assignment. It's quite simple. Think about the fact that you've shifted things, and so we're plotting between 0 and 160, whereas before we were plotting between 1850 and 2010. But I'll let you work this out for the assignment. Actually, it's better if I leave some things to do. And you see, the fit is quite nice. Okay, and I will stop